we're beginning chapter 14, and this one is a really exciting one because it is the last chapter. Not for you, but for me, but because just because of the order I chose to record these videos in, I began at the end of the course, and then I worked my way through the ending of the class, circled back to the beginning, and now chapter 14 is where I finally loop all the way back around, and I will be finished recording the videos. But you are only about halfway through the course. But nonetheless, it's exciting because chapter 14 is the chapter where we actually get the namesake for this class, right? This is chapter 14.1, Functions of Multiple Variables. And that's where we get the title of the class, Multivariable Calculus. So we're really going to start diving into the meat of what calculus in higher dimensions really means and what it looks like and why it's useful in this chapter. And so I think the best way to introduce functions of multiple variables and doing calculus with them is to start all the way back at the beginning like you might have done in 6th or 7th grade and draw some comparisons to functions of single variables. And this should be, I would hope, a review for almost everybody of functions of single variables. But even so, it'll really help to draw those direct comparisons to functions of multiple variables to really understand that this is really just a higher dimensional equivalent of all the ideas you've seen before. So the way I want to begin is I'm just going to color code these notes real quick. So on the left-hand side, I'll do explanations about the single variable function, and then on the right-hand side in red, I will do the multiple variable analog on this side. And so we can draw those comparisons in like a table. So over here on the left, we'll start with just really simple notation. All right, so a function at its basic definition is just a relationship between two sets. And in single variable, we're used to seeing those sets being like the x-axis and the y-axis. So a set of x values and a set of y values. And then we have a function that relates the two. And so the notation we usually see is something like f of x is equal to something, right? And that something would be the relationship that relates x to y. And then an equivalent way of writing that is y equals. And we've seen that so many times that it almost is no longer surprising, or we don't even question why f of x and y are used to be the same thing. But f of x is what we call the function value, and y is just the dependent variable. So x, in this case, in a single variable example, x is the independent variable, and y is the dependent. And another way to think of that is, x is the input and y is the output of the function. All right, and so the two equivalent ways to notate a function could be setting the function itself, f of x, right? That's the name of our function. So that's like the name. Or we could set it equal to the dependent variable, saying like y equals some function of x. And so like an example of that could be like f of x equals 2x, plus 3. And in that case, to evaluate it for a certain value of x, you could just plug that into the function and find the corresponding y value that you get for that x value. And if you notice here, the possible independent variables always occur in these parentheses of the function name. So the function f here only has one possible input value you can put. It's a single x value. And we'll see how that changes in a multivariable function. So here on the right-hand side, I'll start in my red pen, and we'll just do the equivalent of everything we did over here, and we'll see how each of these has a representative thing in a multivariable space as well. So for notation, now we can still name our function f, but instead of being a function of a single variable, it could have more than one variable. So we might have x1, x2, and really, it could have as many independent variables as you would like. There's no limit to how many possible independent variables a function could have, but there will only be one output, right? That's the definition of a function. For a set of inputs or a single input, there can only be one possible output, right? That is a property of a function itself. Now, for example, it could be a 2 independent variable function, and then we would have f of x and y. So the possible inputs is an x value and a y value. So an ordered pair would be the input. And then an equivalent way to write that, just like we could call the function f of x, or we could just say y equals. Similarly, for this case, we could just set the dependent variable equal and call that and call our function that way. So if our inputs are x and y, what would you imagine our function name would be? What would be the dependent variable in this case? Well, for a function of two variables, we typically use z. So z would be equal to something, right? The dependent variable, the output, is equal to some relationship between the input parameters. And right, that's the same thing we had over there with f of x and y. So in this case, x and y are the independent variables, and z is the dependent variable. And so the input, right, our input here is an ordered pair, x and y, not just a single value, but a pair of them, an x value and a y value. And then the output is just a single z value. And then another characteristic of functions is talking about their domains and ranges. And right, the domain, of course, is associated with the input space, and the range is the output space. So for a single variable, right, your domain in single variable functions is all valid x values. Right, so it's x values that you can put into the function and it evaluates. And the range is the corresponding y values for those possible x values in a specific function. So the domain is the set of possible inputs, and the range is the set of all possible outputs. So let's look at an example of how we could analyze the domain of a single variable function. I know you all have done this, but it might have been many, many years before you've explicitly looked at sketching the domain of a function. So really quickly, let's just do an example of sketching the domain of, I'm going to give the function f of x is equal to the square root of x minus 2. And so we know for square root functions, they're limited by the radicand being greater than or equal to 0. So anything under the radical must be greater than or equal to 0. So in this case, we know that x must always be greater than or equal to 2 for the function to be valid. So we could sketch that domain on a number line, right? Because the domain of this function is just the x-axis. It's just x values. So it's a single dimensional input space. So this is we're just going to sketch the x-axis for the domain, and I'll set this value as 0, and I'll pick this to be 2. And then if you remember, the way we indicate a set on this domain is we can just sketch. Let me turn up the thickness of this real quick. Sketch all the values greater than 2 or equal to 2, and we indicate that with a solid dot on 2. Right? If it was strictly greater than 2, we might want to use an open circle to indicate that everything greater than 2 but not equal to 2 is included in the domain. But in this case, 2 is included, and so we indicate that with a solid dot. So that's an example of how we could sketch the domain of this function. And similarly, we could figure out what y values correspond to that domain, and then sketch the range on a y number line. All right, so that's kind of the idea of sketching domains and ranges. And now, in multivariable calculus, the domain for, I'm going to stick with just a 2-variable example right now. So let's imagine we have f of x, y. So the domain in this case is the set of all valid x and y pairs. So now the input space, our domain, is no longer a number line, but instead a coordinate plane. It's the xy plane. So our domain now is, I'm going to draw it like this. Here's my x-axis and my y-axis. And I'm doing it like this so I can add in a third axis up here and they can all be orthogonal. So here's my z-axis. And I can just put in those little squares to indicate they're all at 90-degree angles to each other. But given the broadest possibility, this is our domain. All right, it's the entire xy plane, the entire set of x and y values. And so you could pick, different representative points in this domain, and then they would correspond to a z value. So you pick an x and a y, a point on the xy plane, plug it into your function, and you'll get an output, which is a z value. So it gives you a height, is a way you could think about it for a 2-variable or a 2-independent variable function. And so we could sketch the domain now, not on a number line, but we might sketch the valid domain. It would be on this coordinate plane. So that might be the set of valid inputs for a given function. And in some of the examples I have at the end of this worksheet, we'll take a look at sketching some of those domains. And now I want to spend some time talking about the graphs, how we graph a single variable versus a multivariable function. And so in single variable, right, we typically graph 2 axes, one for the independent variable and one for the dependent variable. Right, so we have a y-axis and an x-axis, x and y, where this is like our independent variables, and then we sketch our dependent variables on the y. And the way we can sketch the graph is pick some representative x values, like x1, x2, x3, and so on, plug them into the function, and we'll get corresponding outputs for each of those. So we might get an output like y equals this y value, this y value, and this y value. And then if we were to pick more and more x values in between those, we would get closer and closer to tracing out what the function looks like. So if we just graph all possible x values in between, we would get a smooth curve, right, that gives us what the function looks like. So these are all the outputs for the domain of the function. And we call this, that is like the graph of our function f of x. So now let's do the same thing for a function of 2 independent variables. So now in this case, we're going to graph a representative f of x, y. So now in this case, we know we're going to need 3 coordinate axes because our independent space, right, our domain is made up of 2 axes. Right, so our input space is the xy plane. Here's our x and our y. And here's our z. So we know that this, here our independent variables live there. Now the independent variables live on the xy plane, and they correspond to a z value. So let's get an example. So let's say we pick just an example, this point, to plug into our function. And that might be the point 1, 1. I don't know, do this just for an example. Maybe the output, right, the z value that corresponds to an input of 1, 1 is, maybe it's there. Maybe that's at z equals 3, a height of 3. Now, could you take a moment for yourself to think of a function of 2 independent variables that when you plug in the coordinate pair 1, 1, it outputs to 3. So I will do this over here as well. So just as an experiment, try to think of some function, f of x, y, that when you plug in 1, 1, you get 3. It evaluates to 3. Well, I can think of one, just set it equal to 3. F of x, y equals 3. That would mean regardless of what variables you input, the output's always 3. And the graph of that would just look like a flat plane at a height z equals 3. Because whatever value you input, right, if you plug in x equals 1 and y equals 4, it doesn't matter. The output's going to be 3, given this example. So that's one. Another one I could think of could be f of x, y is equal to x plus y plus 1. If I plug in the ordered pair 1, 1, that would also evaluate to z equals 3. And so the way we graph a function of 2 variables is just like here, we kind of just pick some representative values of x, graph their outputs, and then, as we pick more and more x values in between, we'll start to get a picture of what the graph looks like. We can do the same thing here, but now we're picking points on the xy plane to evaluate. So you might evaluate all these different points and see what their outputs are. And so we might get for this one an output there, maybe an output there, a z value here. And if we do that for many values on the xy plane, plug all those in and see what their outputs are, we can start to trace out not a curve like we have in single variable, but this would actually be a surface. That's what we call it. And so a surface, it might look something like this. Where all of these input values correspond to a value on this surface. And so you can see that for a single variable function, f of x is what we call a curve. For a function of 2 independent variables, f of x, y is a surface. And you're going to hear that word a lot. So that's where it comes from. Now, another idea is the idea of level curves. And these don't really come up before multivariable calculus, but they're really, really useful for getting an idea of what these surfaces look like without having to graph them. Oftentimes, it can be really difficult to pick enough representative XY values and then graph their outputs to really get a good picture of what the graph actually looks like. And that's why we can use something called level curves. And so level curves, here's their definition. So the set of points in a plane where a function has a constant value, right? We could call that constant value C. So a constant value C is called a level curve of the function. And so the set of all points x, y, and then the z value, or f of xy, in the domain is the graph. So if we graph, right, that's what we were doing here. We were graphing the points in R3, x, y, and z, or equivalently x, y, f of xy. That was the graph, right? That's what we did up there. Here, we're going to take a look at what level curves are. And so a level curve is just a way to visualize what a function looks like, what the surface looks like, without having to construct the 3D shape. And so the way we do that is we just take our function and set it equal to some constant values like C1, C2, C3. And what we're doing is let me draw an example. If here's our x and y axes and z, if our function, right, our surface looks something like this, I'm just going to make up one. Maybe it looks like a bowl. And so that's what f of xy looks like. We're going to set that function equal to a constant z value. And so maybe I'll pick just z equals 3. So if this is z equals 3, then we could kind of slice a plane through this entire surface at a height of z equals 3. Right, so we're setting it equal to 3 as a constant. And we're seeing what shape is that going to trace out if we're cutting that bowl at a constant value of z equals 3. Well, in this case, it's going to trace out a shape that looks like that circle. And now what a level curve is projecting that cut surface, that shape you get by cutting at a certain level, onto the domain. So you're going to take that and just project it straight down onto the domain. And so you get a circle like that on the xy plane. And that's what it says here, right? It is a set of points where the function has a constant value, a set of points where the function has a constant value. And so you know at all of these points on the xy plane, the output is going to be a constant value 3. Here, it's 3. Here, it's 3. Here, it's 3. It's not 3 here. If I were to take this point, then that's going to evaluate to somewhere lower on that bowl. It is only equal to 3 on this curve. And now we could repeat that same process for a different height. Maybe z equals 2. All right, let me do it down here for this one. Oops, doesn't like it when I do that. All right, so now we're intersecting it here at this point. That's also going to trace out a circle. And I know this drawing is getting very busy, but now we can project that circle down too on here. And so if you think about if we did that for a bunch of different constant heights, then we would, if we were to look at the xy plane from above, imagine now we're looking, I'm going to do this next drawing, looking straight down the z-axis onto the xy plane. right? If we're now looking at the XY plane from above, we're going to start constructing these concentric circles that correspond to different z values, right? So this one was like, we did one for z equals 3, we did one for z equals 2, we did one for z, we could do one for z equals 1, and that gives us, without having to know what the three-dimensional surface actually looks like, this level curve plot tells us everything we would need to know about the surface. And so by just being given this picture here, you should be able to construct what the actual surface looks like. And that is the exact idea behind topographic maps. So a topographic map, which you've definitely seen before, is just a level curve of a surface, where your surface in this case is like a mountain range. So here's our surface. Right, this thing could be thought of as our function, f of xy. And let me just like superimpose some axes on here. So in this case, that would be like our z-axis. And then we could have our x-axis here and our y-axis. And you could imagine that if we just pick a input, right, we pick this, let me pick a different one. We pick this value here as like x1, y1, then that's going to correspond to a z value, given whatever that function is, right? It'll have a height outputting to there. And we could do that for every value on the xy plane, and then, we would have some specific function that happens to trace out this exact mountain range, which we could figure out using a computer. And so that would be our function. Now, if we just did the same idea we did over here with level curves, we would construct a topographic map of this mountain range. Let me get rid of this for a second. And so here's our mountain range, and we're going to, intersect a plane right here. That's what these dotted lines are representing. At a height of what does that correspond to? 30 meters? So a height of 30 meters will cut the mountain range straight across, and then we're going to get a curve of everywhere that the height of the mountain range is 30 meters, which would correspond to this curve right here. Something like that, and then it would also be over here. Right, and then it would kind of come behind, and it would be, behind the mountain range over there. And then what was the next step? We take that curve on that plane we sliced through, and we project it straight down onto the domain, the XY plane. So we're going to take that image, project it down, and look, we get our level curve there, right? I think it corresponds to this one. And so you can do that for many, many different values of c, right? Many different constants, and you construct the topographic map. And so that's why a topographic map is so useful, is because by only looking at the domain, the input space, it has all the information you would need to know to reconstruct the graph of the function and know what the surface looks like on a 2D space. And so that same idea can be extended to higher variable functions, but it gets a little bit harder to conceptualize. So I'm just going to spend a moment talking about this, but just so you can understand that this idea can be extended to functions of 3 or 4 or 5 independent variables. So if instead our function looked like this, right, f of x, y, z, then our input space is R3. So you pick a point in R3, and then the output, right, it would be at like a W value in this case. So the output would be a 4-dimensional value, right? And that's why this kind of gets hard to conceptualize. But a way we could actually like look at what a 4D surface looks like, right? This is really cool. The way we could visualize what a 4-dimensional surface looks like is to do the same thing we did here, is to get all the information about a function into 1 dimension lower, right? That was the idea behind level surfaces, is we're taking all the information about this curve or this surface in R3 and containing it, all that information in R2. So now we're going to do the same thing. We're going to get all the information about a 4D surface into R3, something we can actually visualize or draw. And so, for example, right, and before I get ahead of myself, this idea is called level surfaces, right? 1 dimensional higher than a level curve. And so, for example, if I had the function f of x, y, z is equal to the square root of x squared plus y squared plus z squared, right? That is a 4-dimensional function, right? The output would live in R4. Then I could just take level surfaces of it, so set it equal to a constant value and draw what that looks like. So I'm going to set that equal to c. So I'm just going to do like c equals 1. What would be another nice one? 1. Well, I guess 2, 3. I guess yeah, any value would actually work. So let's try that real quick. So then we would get the square root of x squared plus y squared plus z squared equals, let's just try 1. So what does that look like? Well, we can just square both sides and we'll get x squared plus y squared plus z squared equals 1. If we just square both sides. And you should know that parent function is a sphere centered at the origin of radius 1. So let me just sketch that real quick. So if I have my x, y, z, I will quickly just sketch a sphere centered at the origin of radius 1, which would look something like right, that's really bad. But that might be the level surface for w equals 1. And now let's try setting it to 2. We can square both sides, and we'll get x squared plus y squared plus z squared equals 4, right? And so that would be, that would be a sphere centered at the origin of radius 2, right? Because the radius is always the square root of the right-hand side, right? So that would be this sphere, right? This is really bad. But imagine there's a sphere there with a radius 2, and that would correspond with a output value of 2. And so the idea, really what we're doing here, is because we can't visualize the surface in R4, what we're doing instead is we're taking 3-dimensional cross-sections and plotting them in R3 because that's something we can visualize. And that idea is level surfaces, and that's the same idea, but just 1 dimension higher, that we did with level curves. So it's a way to just view what your function looks like without having to construct the entire surface, and you can look at it in R2, right, in your input space. So that's a lot of content to introduce chapter 14 with. I want to stop there and just take a couple moments to work through some relatively easy examples that just applies the ideas that we just looked at. So here, in example 1, all we're doing is we're just sketching the domain for the following functions. And I'm going to go through these relatively quickly. So let's start with electric blue color. Okay, so looking at number 1, sketch the domain of f of x, y, is equal to the square root of x, y minus x minus 2. So what is the restriction for the domain of square root functions? Is we know that whatever, you can't take the square root of a negative number, so the radicand must be positive, so greater than 0. So whatever's under here must be greater than 0. So we'll just set that inequality up. So we get y minus x minus 2 must be greater than 0. And remember, what space are we sketching these in? Right, you always sketch the domain in the space that the domain exists in. So if it's a single variable function, then your domain is sketched on a single dimensional axis. But now in this case, we have a two variable function, so the domain is a two-dimensional space. So we need to do these sketches on the xy plane. So the domain sketches are going to be on the xy plane. Let me come back down here. So let me just set that up real quick. Here's our xy plane, and I just need to sketch y minus x minus 2 is greater than 0. And what does that look like? Well, we can get, let me just solve it for y, because we're used to sketching things as, so y is greater than 2x plus 2. All right, so that's what we're going to sketch. Oops. And so I'll sketch that. All right, I'm getting all over the place. So we rearrange to solve for y, so we sketch, and we'll get, here's like y equals 2, and it looks like that. Oh, and I made a big mistake. Here's the mistake. See, you can take the square root of 0. So it doesn't have to be strictly greater than 0. It could be greater than or equal to. So all of these inequalities should be greater than or equal to. And that means we can sketch this as a solid line because it includes this boundary. And then it's all the values above that line is the domain. So the domain of this function is all ordered pairs that live above the line y equals x plus 2, with that line being included. Okay, let's sketch this one. I'll pick ruby red. So in this case, we have f is equal to the natural log of x squared plus y squared minus 4. So let me just do the exact same thing over here. What is our domain restriction for functions with the natural log? Well, we know that whenever you take the natural log of something, it must, the argument must be greater than 0. And in this case, it must be strictly greater than 0, not equal to. So we know that whatever's in here must be strictly greater than 0. So the way I'm going to get the domain of this is by setting that argument to being strictly greater than 0. So let's just take the inside, x squared plus y squared minus 4 must be greater than 0. I will just rearrange for, well, actually, look at this. X squared plus y squared is greater than 4. You should recognize this parent function. That is a circle centered at the origin with radius 2. So let's graph that. Circle centered at the origin with a radius of 2. So here's our 2. So it must be greater than that. And because it's strictly greater than, not greater than or equal to, the way we indicate that is with a dashed line. So we can say it's must be greater than all of these values. So our domain actually lives out here. So all of these values are valid, not including the boundary, right? Because of the nature of this inequality, must be strictly greater than. And now let's try one more. So the last one we have f is equal to this rational function. And so remember, what is the domain restriction for rational functions? You should all know this. The denominator cannot be equal to 0. right? You can't divide by 0, so we need to indicate the values. Give me 1 second. I need to pick a new color, green. So the denominator cannot be equal to 0. So in this case, the way we restrict the domain is by saying y cannot equal x, right? That fixes this one. And then we also know that y cannot equal x cubed. So those are the domain restrictions. And let's sketch that real quick. So we know that y cannot equal x. So any input that lies on this line cannot be included, so we'll indicate that with the dashed line. And similarly, no points that lie on the line y equals x cubed could be included, because all of those would make the denominator 0. So let me just put that in like this. Here's my line y equals x cubed. And then the domain is every point on the xy plane that does not lie on one of those two lines. Okay, so that should make sense. Okay, in an example 2, this is our last example, we're just going to sketch the level curves of f, our function, given a set of representative c values. So let's do that really quickly here. So in part A, we're asked to sketch the level curves of this function for c equals -3, -2, -1, 0, 1, 2, and 3. So we know that a level curve graph lives in the domain of the function, right? That's where we sketch it, right? Because it's that projection down onto the domain. So in this case, I'm also going to be sketching these level curves on the xy plane. So let me set up some axes. And all we're going to do is set that function equal to our c values and sketch the curve. So we'll do x plus y minus 1 equals -3. Solve that for y, and you'll get y equals, what is that, -x minus 2? Yeah, so -x minus 2, which would give you something like that, where that intersection is right, -2. And so this curve is for c equals -3. Now let's try it for -2. So we'll get x plus y minus 1 equals -2. Y equals -x minus 1. So that's this. And that's for c equals -2. And then we'll keep doing that for each of these c values, and you'll find that they actually are all, let me redo that, all parallel and equidistant from each other. And so what that means is that this surface is just a plane kind of going up like this. It's a plane, and these intersections are at a height of, right, -3, -2, -1, 0, 1, 2, like going up that plane, and then you're just projecting those down onto the xy plane below them. So this is what we would imagine our surface looks like, given that set of level curves. Now let's look at the very last example. This one's a little bit more complicated. So our function is f is equal to x times y, and we're evaluating that for this collection of c values. So let's first try x times y equals -9. I'll solve that for y. So y is equal to -9 over x. And if you recognize this parent function, right, this is just a transformation of that y equals 1 over x graph that gives you the two curves. So I'll set up my axes here. And to graph y equals -9 over x, I know that that's going to be something like this. Right, and I'm not too worried about the scale, getting that -9 kind of dilation. I'm really just worried about the characteristic of what that graph looks like. So this is for, right, c equals -9. And now let's try c equals -4. So we'll get y, right, and you can just do the same rearrangement, is equal to -4 over x. And that would be something that kind of looks like, right, this. So this is for c equals -4. And then I'll do it for, I'm just going to skip a couple of these. For 0, if you do y equals 0, then you actually end up getting just 0. Right, so you just get a point at the origin. So that's for c equals 0. And now we'll do, I'll do c equals 4. Now we will get y is equal to 4 over x. And in that case, you get something that mirrors the -4, but in the other two quadrants. That's for c equals 4. And then c equals 9 is going to be something that looks like this. So that is the level curve plot for this specific function. And now let's just analyze it for a second and see if we can mentally reconstruct what that surface actually looks like. So if you take a look, when c is negative, which means we're slicing the function below the xy plane at a negative value of z, the function lives here and here in quadrants 2 and 4. And when we're slicing the function at a positive z value above the xy plane, the function lives in quadrants 1 and 3. All right, so that's kind of the first thing I notice. And then they kind of have this kind of curved shape to them where it looks like they're never going to quite intersect the axes. So those are the big things I notice. And, you know, with more experience, you'll get quicker at recognizing what these surfaces look like from the level curves. But we can really quickly try to do a rough sketch of what this actually looks like. So I'll set up a 3-dimensional coordinate system so we can graph the actual surface. And so we know, let me throw in some more. So in quadrants 1 and 3, the surface is positive. So it's going to kind of, these are going to get very tricky to draw. And I wish I could have, so it's going to kind of come up like this. And then it's going to do the same thing, right, in quadrant 3, back there. And then in quadrants 2 and 4, it's negative, so it's kind of going down here. And it's also negative over here in quadrant 4. And so, see, this gets really, really tricky. And I think I need to connect them more like this. So they don't go up on the sides. It actually comes like, oh yeah, see, this gets very tricky to draw. But it's going to be some surface that's positive in quadrants 1 and 3 and negative in quadrants 2 and 4, and it kind of gets more extreme the farther away you get from the origin. If you're curious what this graph looks like, you can simply go to Google and just Google in the search bar z equals x times y, and it'll actually pull up a 3-dimensional surface right there in the Google search. And you can take a look at what that surface actually looks like, and it'll kind of look actually nothing like what I just drew here, right? It's going to look much better. But you could imagine taking some 3-dimensional cross sections yourself and getting this level curve plot that we constructed here.